Hello learners, I welcome you once again to Self-Learn channel where mathematics is made simpler and curriculum is implemented. In today's lesson, I would like us to talk about inverse of an element. So by definition, mathematically, inverse of an element A of a set S is of a set S under an operation. This on S is an element whose inverse belongs to the set S such that A operated on A inverse is equal to A inverse operated on A, which is equal to identity element. So the E is the identity element. It means that if you operated a number on its inverse, then they should be commutative and the end result should be an identity element. So let's see how we solve this. Example: a binary operation triangle is defined on the set R or real numbers by P operated on Q, which is equal to P plus Q minus PQ, where P and Q belong to a real number. Find the inverse element under the operation triangle. Right. So let's see how best we can solve this. So we are letting P inverse, which belong to real numbers, be the inverse element, right? So if that is the case, according to the definition, then P operated on its inverse must be equal to P plus P inverse minus P multiplied by P inverse should give us an identity element, right? So we just substitute whatever it is here into the expression given. So because there is identity element here, we have to check for commutativity. So if the operation is commutative, we can say that there is an identity element. So we do that by interchanging the place of this P and Q and putting it into the expression. So since P operated on Q is equal to Q operated on P, so there is commutativity and hence could have an identity element. So we are going to search for that identity element. So to do that, we need to put our rule for identity element. It means that P operated on E should give us what? P, right? So as we learned earlier, right? So we substitute P operated on E into the expression given in the question, this expression in the question. Then when we do that, we have P plus E minus EP, right? And we said this should be equal to P, right? So let's go. So we are saying that this, when we operated the identity on P, should give us P. So this is now equal to this, right? So this should be equated to P. All right, so we have it here. This from here is equal to P from this, right? So the P is from this. Don't be confused where this P is from, right? So we have this, so we have to factor out the E. So when we factor the E, we have this, right? Then we are trying to make the identity element the subject. So we group lighten this, we subtract P from both sides. So here this P is here, right? We subtract P from here, subtract this P from here to eliminate this P. right? So p minus p is 0, and we actually divide through by p1, sorry, 1 minus p equals 0. So we actually divide through by 1 minus p. So I want all of us to understand how e is 0. So we just divide through by 1 minus p. So this will cancel this, right? And 0 divided by any number is 0. That's why the e is 0, right? Good. So from the definition, we say that the commutativity should be equal to what? E. Then our E is now what? 0, right? So let's see what happened. Good. So having this, we put the P and the its inverse in the expression given, and we had this. And from the definition, that should be equal to E, right? So our E is 0. That's why we equated this to 0, right? So we have these two terms here. They are all having P inverse, so we factor P out, right? So when we factor P out, we bring this P to the right hand side of the equation, making it negative P. Then we make P inverse the subject by dividing both sides by 1 minus P, and then we have P inverse to be equal to negative P on 1P. So the inverse element of the binary operation is actually negative P on 1 minus P. So we'll meet again. I say bye bye. Do enjoy your day.